Hello, how are you guys doing? Perfect. All right, we're going to start out with lesson one, and this can be found in your textbook in section 1.1. So the title of today's topic is Bonding and the Shape of Organic Molecules. So what we're going to focus on is what are the organic compounds that we're going to use in this unit. So each carbon atom usually forms a total of 4 covalent bonds. Thus, carbon can attach to as many as 4 other atoms. Okay, first of all, going back to the word covalent. Okay, what does that mean? Remember, it's going to be 2 nonmetals that bond together. We're going to have to go back to a little bit of chemistry from grade 11, so hopefully you can bring some of your memories back. Looking at our carbon atom, it can be found in group 14 on the periodic table. And that means that it's going to have 4 valence electrons. And remember, valence electrons want to pair up with other electrons in order to be stable. So this carbon atom wants to link up with 4 different molecules. Well, it doesn't have to be different, but 4 other atoms in order to be stable. So looking here, we have our 4 hydrogen. Hydrogen is in group 1 on the periodic table, and it therefore only has 1 valence electron. Okay? In order for our hydrogen to be stable, it needs to link up with another electron and have an outer shell of 2 electrons. So hydrogen and carbon are going to link up. So this would be the valence electrons of hydrogen. Oh, that didn't come out too well. Then hydrogen is going to link up with the valence electrons from the carbon. They're going to share those, and that's going to create bonds between the molecules. Okay? Carbon atoms can form strong single, double, triple bonds with other carbons. So here you'll see we have our single bond, our double bond, and our triple bond. Okay? Because they have the ability to have double, triple, and single bonds, it increases the number of possible organic structures. And we're going to learn a lot in this unit. Okay? 2 key words that you need to know we're going to focus on is saturated. Saturated molecules only have single carbon-to-carbon bonds. Therefore, if it's only single bonds, no more bonding can occur. So obviously we would say that this right here is our saturated. However, unsaturated molecules, they contain double or triple bonds. And due to that, there is potential for more atoms to bond to each of these carbon atoms. So I'm going to write unsaturated here for you. Perfect. So, if we look at a molecule like this that has a double bond, right, if we look at that right off the bat, carbon is not stable, right? We only have 2 bonds linked up, and it requires 4 bonds in total. So what we always do is add the hydrogens. So in reality, the molecule would look like this. So what can happen is that double bond is actually highly reactive and can be broken. So let's just pick a different color here. So in can come 2 hydrogens. We could break this double bond, and then the 2 hydrogens could actually attach. And then you see now we've dropped down to a single bond, and we're back to this structure right here. Okay? The same thing can happen with your triple bonds as well. All right. Okay. However, structural diagrams may not show all bonds in the molecule or may focus on only carbon-to-carbon bonds. Okay. If you need help with this, you can refer to your figure 1.2, which can be found on page 6 in your textbook. Okay, so there are 3 different ways to represent an organic molecule. You're going to need to know how to recognize and how to draw all 3 of them. So the first one we're going to focus on is called a completed structure. And this isn't really a good diagram. It actually should have hydrogen, hydrogen, hydrogens coming out rather than writing that there's 3 hydrogens like that. So that would be the complete structure. Obviously, you'd still have your carbon here. This would be your complete structure, and it just shows every single time there's a carbon, every time there's a hydrogen, it shows you every single bond linked up. So very detailed. Sometimes we get lazy. We don't want to draw all those hydrogens. We don't want to draw all those sticks. We can draw something that looks like this called the condensed structure. So obviously these are not the same structures, but the idea is that we're not going to draw out all these hydrogens every single time. Instead, we need to recognize that one bond has already been used up for carbon. Therefore, that allows 3 hydrogens to still be able to bond to that carbon. Same thing here. We can't add any hydrogens to this carbon because it already has 3 bonds here and 1 bond here. Again, meeting its total 4 bond capacity. This carbon right here has 3 bonds already used up with the carbon. Therefore, it can only bond with one other atom, which would be in this case the hydrogen. Okay? Then maybe we're even more lazy and we don't want to write C's, we don't want to write H's, we just want to draw sticks. So then we go to the line structure here. Okay, so the line structure doesn't make a lot of sense right now, but let me break it down for you. Anytime that the lines meet, that would be considered a carbon. So here would be a carbon, here would be a carbon, and here would be a carbon. Anytime it hits the outer edges, that would be considered a hydrogen. So this would be hydrogen. Whoa, that did not work out. Let's try that again. This would be hydrogen. This would be hydrogen, 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 hydrogen. Okay, but obviously we don't want to write those, so you can just draw the sticks and it can represent exactly the same. So throughout this unit, you are going to see a variety of all 3 of these different types. Okay, so you need to be able to recognize those and be able to understand all 3. Okay, continuing on here. Molecules with single bonded carbon atoms are not flat, right? We look at these diagrams we just drew up here. It's not actually how the molecules are going to look. Okay, we need to actually consider their 3D structure. So a tetrahedral shape can be represented with wedges coming forward or dashes receding. Okay, so looking at this molecule right here, clearly there's not a molecule that has A's and B's in it. So an example of this one would be methane, which is CH4. So 1 carbon, which we could say, let's pick a different color. So we could say carbon is in the center, and these B's would represent hydrogens. Okay, so this line right here in front, okay, we call that a forward wedge. That's coming towards us. So you can picture that that hydrogen is pointing straight at you, and then this part right here would be a receding hydrogen that would be kind of going backwards. Again, still hard to tell. It's sort of 3D, but it's harder to get the big picture. This one kind of helps a little bit more. You can kind of see this one's supposed to be heading towards the back. This one's coming near the front. But we're going to actually look at a couple of 3D structures right now, just to give you an idea of some of the structures of what they would look like in a 3D model. So we look at something which is called the Vesper theory. Okay, you're going to have to flip to the pages near the end of your note to be able to follow along. So we're going to flip to the Vesper theory right now. So you should have a page that looks like this. So the Vesper theory, what we're focusing on, let me move down the page. We're focusing on, first of all, how many lone pairs are there? Okay, and then as well, how many are actually bonded up together? So this says we have 3 bonds, which we can clearly see right here, and we have no lone pairs. So whenever that comes into play, so for example here NO3, then we have something which is called a trigonal planar. Okay, and we're going to look at what a trigonal planar looks like in 3D. Okay, so hold on 1 second. So fun. Okay. Almost there. Don't worry about it. I know I'm losing you, but pay attention. 2 seconds. Okay, here, this is a trigonal planar. So here you see we have our 3 bonds. Okay, we rotate it. We can see the 3 bonds that are attached to it. So that's more of our 3D structure. It still looks kind of flat. It does lay on kind of a flat plane. But hopefully this makes a little bit more sense to you of what it would actually look like. Okay, so going back. Okay, the next one we focus on right now is our hydrogen. Sorry, water has 2 bonds and it has 1 lone pair. Okay, this example here they give you ozone, which is O3, but we're going to focus on water because it's very similar. Not actually. Yeah. Okay, so water. So what happens is, actually in water it would have 2 lone pairs. So actually we'd be looking at this one. Sorry, my fault here. That's why we have water here. So you have bent, you have oxygen, and 2 hydrogens that come out to the side here. When that happens, you guys might think it looks like this, which many people do. But because there are actually 2 lone pairs on top of that oxygen, it's going to actually push those hydrogens down to make a bent formation. So let's look at that shape of that molecule. So here we see water. So this is our water molecule. So we rotate around, we can see the different shapes. So at the top there, we would have our hydrogen molecules. And then you would have your lone pairs that would sit like that. So they actually push those bonds down and create that bent sort of structure. Okay, we also have something called a tetrahedral. Tetrahedral is the methane that we just drew before. So you'll see again carbon in the center and you have your hydrogens around the outside. So let's look at the shape of that one. So you have a molecule like this, so it's not flat. You can see them coming, kind of this one's coming out at us. We have one at the back pushing in the receding part. So it looks something like that. Okay, so obviously you see that there's different shapes. So you need to understand that there are, they are 3D and they're not drawn flat like that. I'm just going to show you one more. This one, NH3. This would be considered a trigonal pyramidal. So there actually should be 2 lone pairs up top. Because of those 2 lone pairs, it's a lot different than that trigonal planar we looked at before. It actually, again, is pushing those bonds down, so it creates a little bit more of a different shape. Okay, we look at this molecule, rotate it. Okay, anyway, so look at this molecule. You can see that it's bent, pushes down a little bit, and it's just because of those lone pairs on top. Okay, so let's go back to the lesson. Okay, so you need to be able to recognize those. Definitely when we get to a unit later on in the course, you'll be able to recognize these, be able to name them right off the bat. So you have to be able to recognize just the few ones that I showed you in 3D there. Okay, moving on. Again, this is bringing back a lot of the stuff that we learned in grade 11. We're going to now talk about our covalent bonds, polar covalent bonds, and our ionic bonds. Okay, so carbon to carbon bonds, which we will see a lot in this course, right? We've already been talking about it. And carbon to hydrogen bonds. Those are both considered to be nonpolar, meaning that they basically share electrons equally between the 2 molecules. Remember the definition of anything that is considered covalent and nonpolar? They would have electronegativity difference that is less than 0.5, and that's what this means. It's a change in electronegativity. So the change in electronegativity, what you do here is we're going to look at carbon and compare their electronegativities. So if you go to your periodic table, you can find it in the back of your textbook, or you can use the one that I gave you at the beginning of the semester. We're going to look at this one online just to help you see where the electronegativities come from. This is a periodic table that just has electronegativities listed. So you head over here to carbon, and you'll see that it has electronegativity of 2.55. And you go over here to carbon, so 2.55. We head back to our lesson. You see here electronegativity 2.55, 2.55. We take the difference of those and we get 0. And obviously that is less than 0.5, so they are sharing the electrons between the two of them equally. If we look at carbon and hydrogen, again, we already know that the electronegativity for carbon is 2.55. We can go over and look at hydrogen, and it has electronegativity of 2.20. So if we subtract those two, we get a difference of 0.35. Again, that's less than 0.5. So between those two atoms, they're actually sharing the electrons equally. However, if we look at polar covalent bonds, they have negativity difference between 0.5 to 1.9. What does that mean when something is polar covalent? Well, one atom has a greater attraction for the electrons than the other atom. The electrons therefore lie closer to the atom with the greater attraction. This creates a bond which is known as a dipole. So we have partial positive dipoles and partial negative dipoles. Okay? So if we looked at this example, we have carbon, which is double bonded with oxygen. Okay? And we look at the bond between those two. Again, we're going to look up the electronegativity. So we know that carbon already is 2.55. So we'll go back to our periodic table and look at oxygen. Oxygen we see here is 3.44. So we subtract those two. Okay, and you take the absolute value. You're not going to have a negative value. And we end up with an answer of 0.89. Okay, 0.9 obviously is greater than 0.5, so it fits in the scale that we had mentioned at the beginning of the polar covalent part. So this is considered polar covalent. The one with the higher electronegativity is going to have a stronger pull on the electrons. So the electrons are actually going to sit closer to oxygen, so we call that partial negative. I can't really draw that sign. I just drew an upside down fish, kind of. And we'd say carbon would be a partial positive. So we'll actually rate that. I think it's already in your notes. So this would be partial negative. And this would be partially positive. Beautiful. Okay, so like I said, that means that the electrons are sitting closer to oxygen and farther to carbon. So you can kind of think of it as a tug of war, right? Carbon, oxygen are in a tug of war. Oxygen is a lot stronger than carbon, so the rope that they're sharing between them, the knot that kind of puts the center, is headed closer towards oxygen. And because of that, those electrons are going towards oxygen more. It's more a negative charge going towards the oxygen, which pulls more electrons away from the carbon, giving it that partial positive. Neither one of them actually gives away electrons or takes electrons, and that's why we say it's partially positive and partially negative. Okay. So if we move down here, okay, that's just looking at the actual bonds. So now we're going to look at the molecules as a whole. So is the molecule polar as a whole, or is it considered to be nonpolar? Okay, so keep in mind, though, that not all molecules with polar bonds are considered to be polar molecules. Okay, if they have equal bond dipoles acting in opposite directions in three-dimensional space, they will actually counteract each other. Okay, so let's look at this first one right here. We have hydrogen and chlorine. If we look up the electronegativity of hydrogen, we see that it is 2.20. Okay, so 2.20. We're gonna head back to the lesson. Oh, are you kidding me? Okay, so we look at the hydrogen and we saw that it had electronegativity of 2.20. If we go back to look at chlorine, we find chlorine over here with 3.16. Let's go back to our lesson. 1.6. So if we take the difference between those two, we end up with a difference of 0.96. So obviously this falls under a category of it being polar covalent. Okay, so can you guess right now which one's going to be the partial positive, which one's going to be the partial negative? I can't hear you, but hopefully you said that chlorine would be your partial negative because it has the higher electronegativity value, and hydrogen would therefore be our partial positive. Okay, so that arrow is showing that there's a dipole towards the chlorine, that those electrons are going closer to chlorine than they are to hydrogen. And because of that, it's unequal sharing between those two atoms, and we consider that to be polar. Okay, looking at this molecule right now, I'm not going to look up the electronegativities every time, but you can keep in mind, you should remember this also from grade 11, that as you increase from left to right on the periodic table, your electronegativity is going to increase. So if we look at hydrogen versus nitrogen, nitrogen is farther on the right-hand side, it's going to have the higher electronegativity. So that's why we have these dipoles going from hydrogen to nitrogen. Nitrogen would be your partial negative, and hydrogen would be your partial positive. Okay? Because we have these three polar bonds, we can consider that molecule to be polar. Okay, it's unequal sharing between the two atoms, so it's considered polar. This molecule right here, we have boron and fluorine. If we again follow the periodic table trend of electronegativity, fluorine would have the higher electronegativity, so be partially negative, and boron would be partially positive. So hence why the electrons would actually go towards fluorine more than they would towards boron. And because of that, we have polar bonds between each one of these molecules. So polar, polar. But you might be confused now, why, Miss Hewlin, does it say nonpolar at the bottom then? So if there are equal dipoles acting in opposite directions, that balances the whole thing out and makes it symmetrical. So keyword being symmetrical. So if they have polar bonds, but yet it ends up being symmetrical, we consider that to be a nonpolar molecule. Because in a sense, it is equal sharing throughout the whole molecule. Okay, looking at the next one, we have carbon. Chlorine has the higher electronegativity, so the electron sits closer to chlorine, so that's partially negative. This one would be partially positive. Again, we have that symmetry all the way through it, even though it is actually, polar molecules. Polar bonds. It is considered to be a nonpolar molecule due to its symmetry. Okay, we look at the very last molecule here, carbon and hydrogen. Remember, we learned that before. Those are covalent. You'll always find that carbon to carbon bonds and carbon to hydrogen bonds will always be nonpolar. So right off the bat, we know that there's equal sharing between the carbon and the hydrogen. Hence why there's no dipole and there's no arrow there. So they're sharing them equally. If we look at carbon and chlorine, chlorine has the higher electronegativity, so it would be partially negative, and carbon would be partially positive. Okay, so looking at this, here we have a nonpolar bond, and here we have a polar bond. Okay, obviously making this asymmetrical. Therefore, as a whole, it would be considered a polar molecule. Okay, there's no symmetry between that. The chlorine throws everything off. It gets a little bit more of a pull and pulls it up a little bit, which makes those hydrogens go down kind of on an angle towards each other. Okay? So, we're going to do a couple examples, and then you're going to work on your homework tomorrow in class. Okay, we're now going to flip over to the practice questions. So if you want to get those out and ready to fill in. Here, we're looking at an example problem on page 10. So it says, use your knowledge of molecular shapes and polar bonds to predict whether each molecule has an overall molecular polarity. So here on A, we're going to look at, we have a carbon and a carbon bond. So let's just write out what types of bonds we have to begin with. So carbon to carbon bond. We're also going to have this carbon to hydrogen bond. So remember, going back to note that we learned before, carbon to carbon bonds and carbon to hydrogen bonds are always considered to be nonpolar. So because this whole molecule is filled up with nonpolar atom or bonds, the whole molecule would be considered nonpolar. Okay. Next, as we move down the screen, we have something called ethanol, and you're going to learn how to name all of these later. So let's again write down the types of bonds that we do have visible here. So again, we have the carbon to carbon bonds, we have the carbon to hydrogen bonds, and we also have this new bond here. We have oxygen to hydrogen, and we also have the carbon to oxygen bond. Okay, so reviewing what we learned before again, these we considered nonpolar. However, if you looked up the electronegativity difference between these, it would be polar. So because we have this nonpolar chain here, but we have a polar part at the end, the molecule as a whole would be considered polar. Okay, again, it's not symmetrical. That polar end at the very end is just going to throw the whole thing off and make it a polar molecule. Okay, and then at the bottom here we have trans dichloroethylene. So that has 2 carbons and 2 chlorines and 2 hydrogens. So again, let's write down all the bonds we have. So we have carbon to carbon bonds. We have carbon to hydrogen bonds. Carbon to chlorine bonds. And that's it. Okay, so again, just review, these would be considered nonpolar, and this would be considered polar. Okay, so right off the bat, looking at from our example previously, you'd think, okay, well, this molecule must be polar. It has a nonpolar part, but we also have this polar part that throws it off and makes it a polar molecule. However, we have to look at symmetry. So between the carbon and chlorine, remember that chlorine is farther to the right, so it's going to have a higher electronegativity. Oops. So it's going to have a dipole that goes towards chlorine. If we look at the opposite side, we're going to have an arrow that points up like that. Again, we're going towards the chlorine. If we focus on the hydrogen, they're actually sharing between each other, so nothing's happening. So as a whole, this molecule is symmetrical. So because it's symmetrical, it's opposite charges that are pulling from each other. It actually cancels them out, and then this molecule as a whole would be considered non-polar. Okay? And that's today's lesson.